Hello, how are you, my dear friends? Today, the topic of discussion is the thermodynamics equilibrium. So, thermodynamics equilibrium. Equilibrium means when we move from one point to the other point, but after some time we will stuck. If we stuck, we are neither move forward or nor move backward direction. That this means we attains the equilibrium condition. But how we understand thermodynamics equilibrium? Means equilibrium in case of thermodynamics. How we understand? If we have system like this and we have a piston like this and PVT inside and the PVT external. If we attains pressure for outer pressure and the inner pressure, this pressure is called for the surroundings and this called for system. Okay, in the thermodynamics, study of thermodynamics, if the pressure, external pressure means the P is called like this. If the pressure if the pressure goes equal, then it is a condition of it is a condition of thermodynamics equilibrium. Okay, if the volume and if the temperature, external temperature or the room temperature, means it is also a condition of thermodynamics equilibrium. So what we understand, it means a state at which the thermodynamics, a state at which the thermodynamics variable gets constant for what? For system and surroundings. For system and surroundings. It means we can say it is thermodynamics equilibrium. On the basis of the thermodynamics variable, the thermodynamics equilibrium are the various types. Like if the pressure is constant for the system, if the pressure is constant for the system and surroundings, it is a condition of also a condition of thermal equilibrium. But the name of this thermal equilibrium called mechanical equilibrium. And if the temperature is equal for the system and the surrounding, it's called the thermal equilibrium. So the types of equilibrium is the thermal equilibrium, and another is mechanical equilibrium. Mechanical equilibrium. It means the temperature gets constant for the system and the surrounding. Here, the pressure is constant for system and the surrounding. And another one is material equilibrium. How we understand the material equilibrium? Let us see. Let us see how we understand material equilibrium. How we understand material equilibrium. Let us see. How we understand material equilibrium. Let us see. If we have the chemical reaction, okay, if we have chemical reaction like this is the reactant and this is the product. So material equilibrium means reactant and the product have the same chemical, just like N2O4 convert into 2NO2. Okay, but in other way we can say in the reactant and in the product the material concentration and the concentration for this is same. Means concentration part, if the concentration part gets constant, means it is a material concentration is constant. This is the material equilibrium, and the material equilibrium have two types. Okay, equilibrium have two types. One is chemical equilibrium. One is chemical equilibrium and another one is physical equilibrium. Physical equilibrium means the solid convert into liquid, but for example, ice melts into water. After some time, it attains a equilibrium state. Equilibrium state. After some time, it attains equilibrium state. After some time, it attains equilibrium state. So now we will move forward. So now we will move forward, and so now we will move forward, and we will know or we will discuss some new concept like function, thermodynamics function, thermodynamic function. It is a two types. One is state function and the second one is path functions. Means it is of two types. One is state function and another is path function. Path function means if we move from state 1 here, from here to here via this path. This is a path function via this path. This is a path function via this path. This is a path function. Okay. And if we move from state 1 to state 2, but no matters what path I can follow, state function means the initial and the final state function means the variables in this state function, in this function, the thermodynamics variables, the value of thermodynamics variable depends only initial and final state, just like state 1 and state 2. So the thermodynamics variable is P1, V1 and T1, V2, V2 and T2. Okay. Okay. This is the thermodynamics variables. And here we will write entropy S, enthalpy H, internal energy E or U, also a state function. Okay. Representation is also very important. Okay. So we can represent it. Representation is also very important. We always represent it in capital letter or we can write like this: delta H, delta S, delta U. This is the state function. The value depends only the initial and the final condition. But the path function, the initial and the final value, initial and final value depends on path. If the state 1 and the state 2, this is the path 1 and the path 2 and the path 3. Okay. Okay. For example, we have work is a path function and heat also is a path function, and the representation of work is small w and the representation of heat is small q. The representation is also very important. The path function always represent in a small letter, and we never represent like this small w or delta q. Never write like this. Okay, we never write like this. So this is all about the state function and the path function, variables and the functions. Okay, and the functions, variable and the functions. Thermodynamics function. Okay, this is all about the functions. State function, the initial and final value depends on only the initial and final state, and the value depends on the path. This is called the path function. Okay, now we will discuss thermodynamics properties. Thermodynamics properties, like depends depending on the mass, it is of two types. One is intrinsic and another is extrinsic. Or intensive, 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 or extensive. Intensive or extensive. Okay, intensive or intensive and extensive. Extensive means depends on mass. Extensive means independent of mass. So we know this is very important point. Very important point. We know energy depends on mass. So the all terms of energy, just like for example, internal energy, Gibbs free energy, depends on mass. So it is a extensive property, and heat also depends on the mass. So heat also depends on the mass. Heat and heat capacity, it is also a extensive property. Heat or the enthalpy. Yeah, enthalpy, 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 and heat capacity. And independent of mass, just like temperature, pressure, and here volume also. Okay, temperature, pressure, and concentration. Density, and the concentration is intensive. It means the molar heat capacity, and molar enthalpy is also intensive property, and specific heat capacity is also property of intensive property. Okay, so if we have a room like this and we have pressure, volume, temperature, concentration, and internal energy, enthalpy gives free energy. If we divide it in this, so the pressure never change, temperature never change, concentration never change, but the U, internal energy, is going to be half, enthalpy is going to be half, gives free energy going to be half. Okay, and the volume also going to be half. So if the property changes on changing the, if properties changes on changing the mass, means it depends on the extent or the mass, it is extensive properties. Okay, now we will understand, the heat. Now we will understand heat. Now we will understand heat. What is the heat? Now we will understand heat. Now we will understand heat. Heat means energy. In very earlier classes, we study a reaction like combustion, material and oxygen, ignition. Then we will some product and energy. And energy have two types, just like heat and light. Okay, okay. Just like the CH4 plus O2, ignition, CO2 plus 2H2O, and energy. Energy means some amount of heat and some amount of light. We will already know in the previous classes. So, heat means it is a form of energy. Heat, what is heat? Heat, what is heat? Heat, it is a form, it is disorder, ordered form of energy. Okay, and represented by the Q representation. It is a disordered form of energy. Okay. Okay. Now, what IUPAC said, that how the convention of heat can use. IUPAC convention. IUPAC convention of heat. In the chemistry point of view, we have system like this beaker, and we apply heat here, and our the reaction move forward. Means we have a small system. we have very small system. Okay, so if heat applied like this, heat means if we apply the heat to the system, means it is considered as the positive. Heat given to the system considered as positive. Okay, and if heat, if we have a system like this and system liberates heat, means the heat comes out from system considered as negative. How we can understand, how to remember it? It means, it means we have some reaction pot like this, and if we mix the reactant 1 and the reactant 2 here, okay, and the heat generate, means it is, if heat is not controlled, means it is also a cause of explosion, and we will know explosion is not positive for the human beings. So we will learn here, the heat comes out from system, means heat comes out from this is taken as negative, as IUPAC said that. Okay, as IUPAC said that, means if we apply heat like this, it is plus Q, and if we system liberates heat like this, it is considered as the minus Q. Now, now we will understand the heat capacity. As per the name, heat capacity means capacity of a material to store heat. Okay, as per the name, heat capacity. How much amount of, how much amount of heat it stored. But according to the definition, but according to the definition, according to the definition, to raise the temperature by 1 degree centigrade, the amount of heat required, definition क्या हो जाएगी? What is the definition? The amount of heat, the amount of heat, the amount of heat required to raise the temperature by 1 degree centigrade. Okay, raise the temperature by 1 degree centigrade means in this line we have some material, means the mass, and increase the temperature like this. Increase temperature means that change in temperature by 1 degree centigrade, and we have heat like this. So if we formalize this, means Q is directly proportional delta T, M in delta T. If we remove the proportionality constant, means Q is equals to M C delta T, means the C is a proportionality constant, and we can say the C is what? C is heat. C is heat capacity. C is heat capacity. Okay. C is a heat capacity. So C is heat capacity. So we have formula Q is equals to M C delta T, and the C is equals to Q by M delta T. Okay. Now, if we amount, fixed the amount of material, means if we consider the mass is fixed, means if the mass is equals to 1 molar, means mass is if the mass getting fixed means 1 molar, if the mass getting fixed 1 molar, so it is called the molar heat capacity. Now definition is what? The heat, the amount of heat required, the amount of heat required to raise the temperature by 1 degree centigrade of 1 mole of substance. Okay. Now the formula, if the Q directly proportional to M delta T and M convert into mole, so Q is directly proportional to N delta T. Okay. And if we remove the proportionality constant, then Q is equals to Cm N delta T, means the formula Q is equals to N Cm delta T. Okay. Our amount gets fixed for the 1 molar, then the notation of the heat capacity gets changed, the Cm for the molar heat capacity. Molar heat capacity. Okay. Now, if our amount, if our amount, if our amount gets fixed, but not in mole, if we change the unit, if our amount gets fixed, if amount get fixed, means it considered as 1 gram of substance. Okay. Now So it will consider as a specific heat capacity. Now, what is the formula? Meaning, what is the definition? The amount of heat required, the amount of heat required to raise the temperature by 1 degree centigrade of 1 gram of substance. Okay, so we know the heat is directly proportional to m delta T. If our mass gets fixed for 1 gram, means if we convert it 1 gram, so if we remove the proportionality constant, then the new constant introduced here S and M delta T. Okay, so if we combine the all heat capacities, if we combine all heat capacities like this, so we have formula like this: Q is equals to M C delta T, or N C M delta T, or M S delta T. Okay, this is the mass of substance. ये heat capacity. This is the number of mole. This is the molar heat capacity. This is the mass of substance, and this is a specific heat capacity. Okay, so we have the three types of heat capacity, like molar heat capacity, specific heat capacity, and heat capacity. If we fix the amount, then we introduce the two another type of heat capacity, just like the molar heat capacity, and another is the specific heat capacity. So we will meet in the next lecture.